Hi everyone. Today I'm gonna introduce an overview of transformers, one of the most significant advancements in deep learning. Transformers have revolutionized fields such as natural language processing, called as NLP, and computer vision, called as CV, enabling models like ChatGPT, BERT, and DALI. In this video, we will cover the core principles of transformers, their architecture and training process, their real-world applications, and finally current challenges and future directions. Alright, so what is the transformer? The transformer model was introduced by Google in 2017 in the paper Attention is All You Need. It is a deep learning model that has become the foundation of modern AI applications. Unlike the traditional models such as RNNs and LSTMs, transformers can process information in parallel, making them faster and more efficient. Also, they are highly scalable and can handle long-range dependencies effectively. So, why transformers? Before transformers, recurrent neural network, called as RNNs, and long short-term memory, called as LSTMs, were commonly used in NLP. However, they had several limitations. First, long-term dependencies were difficult to capture. Second, slow training due to sequencer processing. Therefore, as a solution, Transformer introduced the attention mechanism, allowing parallel computation, which is significantly improving the speed, and better long-range dependency handling, which can understand entire sentence more effectively. Let's move on to the core principles of transformers. The key principles behind transformers are first, parallel processing. Unlike RNN, which process words sequentially, transformers process the entire input at once. Therefore, as an advantage, it is faster at training and inference. Second, it goes with the attention mechanism. Instead of treating all words equally, it focuses on the most important words in a sentence. As a result, in advantage, more accurate understanding of context is possible. Third, solving long-term dependencies is like this. For example, in the sentence, the book I bought yesterday was very interesting, the word book appears at the beginning, but the interesting appears later. The transformer learns these relationships effectively. Next, let's look in the transformer architecture, which is encoder and decoder structure. The transformer consists of two main components. First thing is encoder, which processes input, text, and extracts meaningful features. And other thing is decoder, which generates output based on the encoded information. Let's talk about key components. There are three components, which is multi-head attention and feed-forward network called as FFN and positional encoding. So the first thing, multi-head attention identifies important words in a sentence. The next thing, FFN, goes with further refines context understanding. Finally, the position encoding maintains word order information. Next part would be the word embedding, that how words are represented. So before that, what is word embedding? It transforms words into numerical vectors, allowing the model to understand the relationship between words. Let's go into the example. If you see the formula king minus can plus woman equal queen, this represents semantic relationships in a multi-dimensional space. There are two types of embeddings. First thing is static embedding, and second is contextual embedding. Static embedding is fixed vector for each word. For example, there's a track and there's some certain numbers. However, contextual embedding changes based on the context. So, for example, in the track in railway and the track in follow are not in the same meaning. Transformers use contextual embeddings for more natural language understanding. Next part is attentional mechanism, which is understanding word relationships. Instead of treating all words equally, transformers assign importance scores to different words in a sentence. For example, if there is a sentence that the cat sat on the mat, the word sat relates more to cat than mat. The model prioritized key relationships accordingly. There are also three mechanisms: query, key value mechanism. So the first concept, query, which is called as Q, is what we are searching for. For example, book in the sentence. The second one is key, which is called as K, is word in a sentence. For example, I bought a book. Finally, the value called as V is the actual word representations. For example, book is interesting. Next part is multi-head attention. So why multiple attention heads? A single attention mechanism captures only one aspect of a sentence. Therefore, as a solution, we came out with the multi-head attention. Each head attention head focuses on different relationships, making the model more powerful. For example, if there are three heads, the first head will go with the grammatical structure. For example, the cat said. And the second head will go with the semantic meaning. For example, cat relates to animal. Finally, the third head will go with the sentence meaning as a whole. For this advantage, there are more diverse learnings, so we can make more accurate text generation. Now, let's look into how transformers are trained. There are a step-by-step process. There are overall 6 steps. The first one is data collection. We can collect data like Wikipedia, books, internet text. Next thing is tokenization. So basically splitting the words into subwords. For example, learning goes to run plus ing. Next part is embedding. So converting words into numerical vectors. Next part is attention mechanism, which is learning relationships between words. Next part is softmax prediction. This is selecting the most probable next word. Finally, backpropagation and optimization, which are adjusting weights for accuracy improvement. Alright, let's see about the large language models built on transformers. There are popular transformer-based models such as GPT-3 or 4 or the BART. Do you guys know why they are powerful? This is because they are trained on massive data sets such as Wikipedia, books, or online text. Also, they generalize well across various tasks like translation, summarization, and text generation. Let's go into real-world applications of transformers. Where are transformers used? The first thing is chatbots and virtual assistants. For example, ChatGPT or Google Bard. They can also used to image generation, such as DALL-E or Midjourney. They are also used for automated translation, such as Google Translate. And finally, they can use as medical AI. AI-assist diagnosis in healthcare will be proved. So for example, this is the DALL-E, and DALL-E can generate realistic images from text descriptions. This picture is made by the prompt that I just make an order to draw some 20th Korean boy working with computer really hard. Alright, let's go into the final part, challenge and future improvement. There are two current challenges. First thing is high computational cost. It requires powerful GPUs and TPUs. The second part is data bias, so training data can reflect societal bias. And next thing is future directions. So we need to develop efficient transformers. Models like Reinformer and Performer reduce computational cost. And we need to think about ethical AI, basically reducing bias and making AI more responsible. Alright, this is all for today, and we're gonna summarize the whole content before ending. Transformers revolutionize AI with parallel processing and attention mechanisms. They power state-of-the-art AI models like GPT-4, BART, and DALL-E. Future research aims to improve efficiency and fairness in AI systems. Alright, this is all for today. Thank you for your attention.